This is Math 251, section 13.7. We're now going to look at a topic that you're very familiar with in a single integral situation, but that we haven't addressed much in terms of the doubles and triples, and that's change of variables with a substitution. In a single integral, we had u substitutions, and u substitutions still happen when we evaluate specific steps of a double or a triple integral, but they don't take care of the entire integral. And it's that whole big picture that we're going to try to come up with this time. Just as a reminder, when we do a u substitution, typically what we do is we think of our u as a new function of x, or vice versa, x as a new function of u. And then we always have to look for that derivative somewhere in our integral. The equation x equals g of u, in other words, the inverse of our u equals f of x equation, can be described as the transformation equation that describes that change of variables. Why do we normally do a change of variables? Well, essentially we do it to make it easier, right? We're trying to make the integrand into something that we can integrate. The one thing I'd really like to focus on right here is that when we do a u substitution, every time we do it, when we change our variables, we always end up with this extra little piece. Right? We always end up with this derivative piece out here. And that derivative piece is what allows the change of variables to work. We need to find out if there's some sort of an equivalent in a double or a triple integral. In fact, for the purposes of this class, we are going to concentrate just on double integrals. Your book actually talks a bit about triples as well, so if you're interested, you can read that, but I'm only going to talk in this video about doubles, and you're only responsible for doubles in terms of the homework or tests. So, let's see if we can figure out the multivariable version of substitutions. Here it is. I've actually kind of just written it out and given it to you here. If I have a function f of x and y, and I want to integrate it dA, dx dy, or dy dx, over a region R, then I can change the variables instead of x and y into something with u's and v's. This thing is the multivariable equivalent of that. It's that extra kind of fudge factor, if you will, that allows the change of variables to work. It makes the integral come out correctly. So we'll need to talk about exactly what that is. But in your mind, just think of that as that extra factor that often comes about as part of a substitution. All right, what are our transformation equations in this case? Well, you can see that I've replaced the x with g of u and v, and I've replaced the y with h of u and v. So these are my transformation equations. Sometimes we call this set of equations capital T, T for transformation. Now, we're ready to talk about this thing. The Jacobian of T is defined as the determinant of the matrix that you get when you take the derivatives of x with respect to u and v, and the derivatives of y with respect to u and v. And notice it's the absolute value of that Jacobian that ends up as part of our integral. If you like to write that with a little bit of shorthand notation, you could write that as x with respect to u, x with respect to v, and then y with respect to u, and the derivative of y with respect to v. To evaluate this 2 by 2 determinant, we just do our downward diagonal, x sub u, y sub u, and subtract our diagonal in the other direction, x sub v, y sub, whoops, I'm sorry, I miswrote. That should have been y sub u, y sub v. So we have x sub u, y sub v, minus x sub v, y sub u. There we go. I don't usually use this formula anyway. I just usually multiply them and subtract. All right, so let's take a look at one of these that you have actually been using for a while, but you may not have known it. We're going to look at the change of variables that we always use when we integrate in polar coordinates. We all saw a while ago, and we saw it geometrically, that if I want to take a function that's set up to integrate in rectangular coordinates and change it to polar, I can't just replace dx dy with dr d theta. I had that extra factor of r, right? It's r dr d theta that became the dA. We saw where that r came from geometrically, but I'd now like to look at where r comes from, thinking about it as a substitution. So here we go. We know that our transformation equations are x equals r cosine theta and y equals r sine theta. Instead of u and v, in this case, I have r and theta. So my Jacobian is going to be the determinant of, again, not u and v, but r and theta. So x sub r, x sub theta, and y sub r, y sub theta. The derivative of x with respect to r is just going to be 1 cosine theta. And the derivative of x with respect to theta is going to give me a negative r sine theta. Next row, y with respect to r is 1 sine theta. And y with respect to theta is going to be r cosine theta. Multiplying the main diagonal, I have r cos squared theta. Subtract. Multiplying this diagonal, I have negative r sine squared theta. If I factor out the r, I have cos squared theta minus a negative or plus sine squared theta. And of course we know that's just 1, and r times 1 is still r. And so there it is. That extra factor that we get from the Jacobian is an r. And so when I go to change my integral, I end up with that extra factor of r in there when I move to dr and d theta. So not surprising, because you've seen it before, but we can see it using this new method, which hopefully helps you, since I haven't proven this method to you, just kind of verifies that it seems to be working. All right. How are the regions R and S related? We saw this region R for the variables x and y gets changed to some new region S for our new variables, in general u and v. But let's look at that specifically for the rectangular and polar situation. I'm actually going to switch these around. I'm not as happy as I wanted to be with my little table here. I need to switch that in my notes next time. But let's go ahead and do the region in the r theta plane here. And then we'll talk about the region in the xy plane over here. And this is no longer really specifically example 1. I'm just going to make up an arbitrary region in the r theta plane and look at what it looks like in the xy plane. So let's, in the r theta plane, think about a pretty nice simple region. I'm just going to go with a piece of a circle. Oh, excuse me. I just did it again. I'm in the r theta plane. So let's think about a nice simple rectangle in the r theta plane. I'm going to go from 0 to 2 on my r-axis, and let's take our thetas from 0 to pi thirds, even though I kind of gave away the ending there. This would be the region in the r theta plane. Now, in the xy plane, I'd like to think about what happens to each of my sides of my rectangle as I change the pieces into the x's and the y's. So rather than just making a really quick generic change, I would like to actually follow the individual pieces with our transformation equations. So I'm going to start with this bottom of the rectangle. And for the bottom of the rectangle, let's calculate both starting and ending values. We know here that theta is going to start at 0, or actually theta is going to remain 0 for the entire time, and that r is going to go from 0 to 2. So I'm going to start at r equals 0, theta equals 0, and I'm going to end at r equal 2, but still theta equals 0. So x is r cosine theta, which is 0, and y is r sine theta, which is also 0. I start at the point 0, 0. When I end, x is 2 cos 0, which is 2, and y is 2 sine 0, which is 0. So far, nothing too startling has happened. I've started at 0, 0, and I've ended at 2, 0. And this looks a whole lot like the exact same line we had over here in the r theta plane. But I'm now working with the xy plane. All right, let's try the next piece. I'm going to do this right-hand side of the rectangle next. And for that right-hand side, let's see. R remains constant. R is equal to 2. But theta goes from 0 to pi thirds. So again, if I think about a starting and an ending, I start at r equal 2, theta equals 0. So x is 2 cosine 0, or 2, and y is 2 sine 0, or 0. And then for ending, I end at r equal 2, theta equals pi thirds. So x would be 2 cosine pi thirds. Cosine of pi thirds is a half, so that's just 1. And y is 2 sine pi thirds. Sine of pi thirds is the square root of 3 over 2, so that just comes out to the square root of 3. So at 1, let's call that square root 3. There I am. And this is actually that arc of the circle that radius 2. Keep in mind, r was 2. R was constant in this entire thing, so we still have to keep that r equal 2. It's that piece of a circle that connects this point 2, 0, and this point 1, square root 3. All right, I'm going to think about the top now. On the top here, let's see, theta is pi over 3 all the time, but r goes from 2 to 0. So let's see, we start out with r equal 2, theta equal pi thirds. It's really the same as this, but I'll write it out again real quick. R is 2 cos pi thirds, which is 1. and x is 2 sine pi thirds, which is the square root of 3. So I start right where I left off, which is a good thing, right? And then where do we end? R ends at 0. Theta is still pi thirds. But that means x is 0 cos pi thirds, which is 0. And y is 0 sine pi thirds, which is also 0. So I end at 0, 0. Back where I started. Now this might seem a little bit weird because we still have an extra triangle over here. So let's finish, or excuse me, not a triangle, an extra line segment over here. So let's think about what happens with that line segment. On that last line segment, r is always 0, and theta goes from pi thirds to 0. Since r is 0, however, keep in mind whether I'm doing r cos theta or r sine theta, doesn't matter what theta is. I'm going to get 0 every time, right? If r is 0 and theta is pi thirds, x is 0 cos pi thirds, which is 0, and y is 0 sine pi thirds, which is 0. When we end, r is still 0, but theta is now 0 as well. And the same thing happens. I get 0 for x, and I get 0 for y. So I'm at 0, 0 to start with, and I'm still at 0, 0 when I finish. This entire line segment is actually mapped to just that one point at the origin in the xy plane. So here is our little circle sector that we're very used to seeing when we do regions in polar coordinates. And using our new transformation equations, we can very literally see how a rectangle corresponds to a sector of the circle, which is why these are often called polar rectangles. All right, we will do a couple of actual examples start to finish in the next video.